partnership with WWCode. We really want to welcome you. Just give yourself a clap for making it to KL today. Good job, guys. We're very, very happy to have you here. We just wanted to give a shout out, especially to the ladies who are here today. Can everyone just give them a clap as well? Right? Because this Friday is International Women's Day, and I think today is a great time to have this event as well. So just in case you're wondering who is this intern-like person standing in front of you, talking about women, my name is Ming. I'm in the Young Talent team, and part of my role here is partnerships. And our partnership with Women Who Code goes back quite a while. But most recently, we connected again, and when they asked us whether we wanted to partner on this event, we really jumped on board, and we're very happy to actually work with them. And they are a bunch of cool people who have day jobs but dedicate a lot of their time for activities like this. And so we just want to give them a good shout out as well and a clap as well, guys. Okay, so just a few house rules. For those who need to go to the toilet later, you might be wondering, where is the toilet here? On this floor, we have the ladies' toilet. So as soon as you go out of these entrances, you just head this side, and that one will be the ladies' toilet. For the gents, unfortunately, you need to exercise a little bit more. You just have to go on one floor, that side. So don't try to access it from this side, because it's not connected. So go that side. Okay, for those who have not had enough to eat, no worries, we will pack some food outside so that you can bring back as well. Okay, but just so you know, just in case we brought in some food, we prefer strongly that there is no food inside this hall. If you have any drinks here, mineral water is fine, but any other drinks, it's better to consume outside as well. All right. Remember to silence your phone, put it in vibrate, because today we also have a live stream going on. So whoever's in the hall, you're not the only one going to view. We're also trying to extend this to people outside so that they benefit as well. Okay. So without further ado, I want to introduce Daphne, who will come over from Women Who Code to MC the event. Welcome.
Hello everyone, I'm Daphne from Women Who Code, Kuala Lumpur. So a little bit of introduction. Women Who Code is a non-profit organization started in San Francisco, and we are the Kuala Lumpur chapter started by Jesslyn and Jean, who's not here today, but Jesslyn's here. And I'm with my fellow Women Who Code leads and directors here that are in the front row. Maisie helped organize this Maxis event with us today. Because she is also a data scientist and she's very passionate in this field. So Women Who Code, we aim to promote a technology career for women by supporting them and offering evening talks like this, AI or Agile or any kind of tech talk, maybe cloud. We also hold weekend workshops like JavaScript or Python. We have a Python series. We just had 105 recently, so that was great. We are also having an International Women's Day party on the 19th of March, and it's very near here. Common Grounds, Bukit Bintang. It's a paid-for event, but we aim to get to know our network members a bit better by having a chit-chat session, maybe some game session, and get to know each other. Okay. So today we have a series of very interesting AI talk, and I would like to introduce our first speaker. It's Miss Fairoza Amira Binti Hamza, or also known as Miss Rosa. She is currently pursuing PhD in the Information Science and Control Engineering in Nagaoka University of Technology, Japan, and expected to graduate at the end of March 2019. She will be working as an assistant professor in the Kyoto College Graduate Studies of Informatics in Kyoto. Japan from April 2019. She has internship experiences in University of Warren in UK, Panasonic in Japan, and Google Inc. in Japan as well. So with her wide experience, she would like to share with us about the past, present, and future of image compression. Any questions, just go to the Slido, sli.do, and enter the code AI-Maxis. So you can type in your questions anytime, and we will try to answer as many as possible. Thank you.
Should I just start? Oh, where? Okay. Okay. Can on my slide maybe? Okay. Hello and good evening, everyone. Can you hear me? It's okay? Okay. My name is Fairoza Amira binti Hamzah. Okay. Let's wait until my slide come out. Where is the? Oh, I should change. I should touch this one.
Yeah. Yeah.
Oh, this one. Oh, this one. Okay. Nice. How?
I think you can pick this up and use the mouse.
Just use.
But this one can
for the live stream.
Yeah, but this one can hang somewhere. Then you can use it. Yeah.
Yeah, sure. You can do that. It's okay.
Sorry, guys.
Can. Go. Sorry. Boleh? Kan? Jatuh tak? Sebab tak bawa poket ko punya. Oh. Cannot hold. I already have like a lot in my hand.
Sorry guys.
Okay, nice. Sorry about that. Okay. Today I'm going to talk about the past, present, and future of image compression. Actually, this picture was taken by me last autumn in the place that I live in Nagaoka. So it's very nice picture, right? So how do you want to compress this kind of picture is what I'm going to not teach, is just like sharing an information, because I know like everyone still not familiar what the compression is about. Okay, before that, I would like to introduce myself. Okay, my name is Fairoza Amira binti Hamzah, and I'm from the twinning program actually in Unicell. Like I'm under the Mara scholarships, and I just start from diploma, bachelor's, master's, and then PhD until now, and then I'm going to grad this end of March. So basically, I already finished my PhD, and I'm on my holidays. Thank you very much. But as we know, like it is lifelong learning, right? So after I just finished my PhD, I go for the deep learning nano degree that's sponsored by Facebook, and I have like few internship experience. I've been to Panasonic and UK also, so I know a little bit of culture in UK, how they do the computer science, and also to the Google. And if you want to work in Google, you can ask me how to work in Google. It's quite difficult actually, but I think Maxis is much better. You can work in Maxis, and I will be sorry about that. And then I will be working as assistant professor in the Kyoto College Graduate Studies of Informatics. I will be teaching master and undergrad students. We have English course, so if you want to go for master, just go under me. And then okay, you can contact me through this one. Where is the laser? The laser. Oh, it doesn't work in here. Okay, sorry about that. Okay, you can contact me through LinkedIn or just email me directly. Okay, now we want to talk about image compression. So in your smartphone, in your PC, you're going to see the .jpg, right? That one is the image compression standard. So why we need to compress the image? I think everyone already know about that, because we have various type of data. We have the text, we have the still image, we have the video, we have a lot of image. And right now, if you are doing the reality or VR, they're using the 4D or 5 dimension. Like the light field image that is used for the 3D television, it's the 7D usually, 7D. There's a lot of dimension. Usually you just see the spatial dimension X, Y, Z. and then it's being used in temporal dimension. But in 7D, they have a lot of angles that if you're going to study about that, you will know about this. So this type of data will have a lot of file size, like this one. We can see here. Oh, this slide is become like this. Okay. For the CT image, this is for the 4D CT. The uncompressed file size means the file size that is not compressed yet, that is not being transmitted to you yet. The original one, the raw one that you take from your camera. Like in camera, they will have raw images and compressed images. So the uncompressed will have like 1 gigabyte. And for MRI, the 3D MRI is 50 megabytes, and the 4K still image 4K. Like the resolution is 4522. The uncompressed file size is 35. So imagine if we have a video, a 4K video. So one frame is like 60 frames per second or 30 frames per second, right? So 30 times 35, how much will it get? And it will get a lot. And then right now we are in the big data society. So you need to have a lot of data set. If you are doing the image recognition, something like that, image classification, the regression problem, the data set are very big. So if you didn't use the image compression, then you cannot transfer the data very good. So in image compression, you have a very huge file size, and then you need to compress the image, and then the one that you get to see in your device, in your PC, is actually the one that already being restored. So I will explain to you about this later, with this kind of restoration. Like, we need to restore the input data without any loss of with accepted perception loss. So the most important, the main goal in image compression is to reduce irrelevance and redundancy of the image data in order to be able to store or transmit them in the most efficient form. So there are two types of image compression. It's the same like data compression. Like we need the lossless and lossy. The lossless usually being used by the medical image, the one that you don't want to lose any data. So it's reversible, large compressed image size, and like the reconstructed image will be the same like original image. But in lossy, it's irreversible. Usually people now use the lossy compression. The lossy compression for the entertainment, the one that you see in the TV. So it's have smaller compressed image size compared to the lossless. So now let's go through to the international standards of data compression. Let's just go through into the 2D and 3D signal. Let's not go into the 4D, 5D because it's going to be more complicated. So for the 2D signal, the pioneer one was in JPEG, the JPEG. It was like when I was born 27 years ago. It's already 27 years that you are using in your phone right now, the JPEG. And then after that, JPEG XR, JPEG 2000, and then JPEG XR. JPEG XR is for HDR image, the high dynamic range. And then the BPG. BPG is actually the intra prediction. It's a part of HEVC. HEVC is for the video, so they use it for the still image. And then the latest one is JPEG XS. JPEG XS is still under research, 2016. And for the video, volumetric image, for the 3D signal, like the first one is H261, and after that, the latest one is HEVC, the high efficiency video coding. So the one that you use in your smartphones right now, if you are using the latest one, the Apple or whatsoever, you are using the HEVC. So other than that, people are trying to research on how to compress the holographic image. Because in the future, you're just going to see, oh, this is a screen, and you didn't see the screen inside your phone anymore. So they are trying to do this. And the light field image in 2016. So this is what they already do. So how to do the image compression? There are three steps. Which is the prediction, quantization, and entropy coding. So the one that already, if you're an undergrad student, if you take the information theory course, so you already know a little bit about this. You have an original image. You need to transform them. The transform part is like Fourier transform, something like that. You need to classify the data into the high frequency and low frequency. So in here, we are doing the energy compaction. Energy compaction means like you need to compact more energy so that you can save a lot in the low frequency part, in the detail part. And after that, you are going to reduce the unnecessary information by quantizing it and then entropy coded it. This is called the binarization, where you are going to transfer them into the bit stream and then store, transmit, and you will get the reconstructed image. But the quantization is for the lossy compression only, not for the lossless. So my research study, is focusing on the transform coding. So I'm very familiar with transform coding compared to the quantization and entropy coding. So transform coding is to choose the information to be discarded. There are a lot of conventional methods for such as the KLT, TFT, DCT, DST, and DWT. For those who didn't know what kind of transform is this, if you know the basic of Fourier transform, this is the advance of the Fourier transform. So the KLT, everything they use the pre-processing is block splitting. The block splitting will cause what you see in your image if you see a videos in 240p and suddenly you see a lot of blocks. That is the effect of the block splitting, because you need to reduce more information by split the block first. Then it's very easy to transform something like that. Oh. Okay. Okay, sorry about that. So they use the agent decomposition, and then the DCT and DST using the matrix multiplication, and the WT use the subband coding. My study is on discrete wavelet transform. I will tell you later why I use the discrete wavelet transform. So this is the energy compaction property. Okay, if you're not very familiar in the mathematics side, so do not look into the equation, it's very difficult. Okay, just see in the energy preserve and the block size. The block is the first that you split first, right? Okay, so the more you split the block, so the more there will be like a lot of energy preserved, but after that it will become flat. Then the best one is KLT, then the DCT, and then the wash and hard. It's kind of transform also. So KLT is known as optimal transform coding. So this is the DCT. DCT is derived from DFT. This is the coefficients of DCT, basis function, and then multiply with the image, with the block. And you will get, okay, that one is the high values, mean low frequency details information, and low values, the high frequency. You need to set in your mind that low frequency will have detailed information and high frequency will be lower detailed information, like unnecessary information. Usually in transform, you just want to discard the high frequency. So in DCT, they do like this to discard the unnecessary information. And then this is the KLT, the optimal transform coding, but they have the disadvantage because you need to transmit the KLT matrix, the eigen decomposition that you've done in KLT. If you know the principal component analysis, means like you're finding the median of each values there, then it's the same like the PCA. And then this is the GFT. GFT is the latest one. It's being researched like 2-3 years ago. And then the advantage is non-fixed and can fully exploit the diverse statistical properties of the image block. And the disadvantage over DWT is the basis, the eigenvector needs to be sent to the decoder. And then this is what I'm studying about, my PhD dissertation. It's localized in both time and frequency, and then it provides a multi-resolution. The advantage is it is whole image analysis, meaning you don't have to split into small blocks. So it's much more faster. It's like you don't have the blocking artifact. If you are using the JPEG 2000 to compress your image, you will not see the blocks. So this is the advantage. Like usually people will compare between JPEG and JPEG 2000, the DCT and the WT. So the basis for the DCT, all bases have the same length, and the WT, they are long in low frequency and short in high frequency, so they will not have blocking artifact. So what is the advantage over the other compression methods? Even the latest one, the deep learning one, is they have the low computational complexity. That's why people are still not using the deep learning for the image compression. So this is the image compression standards. Like we have BPG. It's really intra-prediction. The intra-prediction is going to get the residual only to transform. So go to the DCT, DWT, quantization, and entropy coding. So this is my study actually. If you want to do the lossless compression, just now, still remember like lossy will have a lot of loss, and lossless will not have any loss. It will be just the same from the reconstructed and the original image. So we need to use this integer transform actually. You can see here like the recovered signal will be the same with input signal, because in here you have minus, right? So in here is plus back again, and there is plus and minus back again. So what you put, you will get back. So that is called what the integer transform. And we have the rounding operator there, and my PhD dissertation is in this part actually. on making the 4D for the integer wavelet transform. So you're going to get the low frequency and high frequency. The low frequency part is the most information there. So it's a key to the lossless compression. So this is my PhD dissertation. You can refer more in the LinkedIn. No, I have a lot of paper. You can read one of that. And then this is the non-sparable and sparable. What I did is I reduced the rounding operator so that I will get a high coding compression, coding performance. And of course, I also reduced the latency, which is the processing time, because you don't have to do one time like the sparable one, which is the JPEG 2000, the normal JPEG 2000, you need to calculate one by one, but here you just calculate at one time. So I can just reduce the lifting step, the latency of this part. So let's go through to the deep learning in image compression. So the deep learning in image compression is very new, totally new. They start in 2016 or 2017, something like that. Because it's very difficult, not very difficult to do, because it has a lot of drawbacks. Because if you want to compress an image, you need to do it faster. But if you do the image classification, you don't really care about the processing time. What you really care is the result. So it's totally different from the image compression. So in deep learning, in image compression, they use the non-linear transform coding. How they do that is almost the same with the linear transform coding, but they add some stuff in there. So if you are very familiar with deep learning, they have the autoencoder. Autoencoder is dimensionality reduction in this part. It's similar to principal component analysis. So it minimizes the same objective function as the principal component analysis. So let's see, this last year, Google, Twitter, Netflix, they do the CVPR CLIC 2018, a challenge on learned image compression. And if you are very interested in image compression, you can try to enter this challenge. It has like, let's go through which one get the best MOS, best SSIM, best PSNR, and the fastest one. So this is the fastest one. Fastest one, it uses the conventional codec. It's block space, it's traditional approach, and originally developed for video compression and no machine learning involved. Yes, it's fastest, right? Because no machine learning. So when machine learning involved, it will not get the fastest one, but the result is very good. So this one is the best MOS and MS SSIM. SSIM is like how much you are going to see the image the same. Means like you're comparing two images, like the reconstructed and original, which one is almost the same. That is SSIM. So they use the autoencoder inside that and use the 4-bit quantization, soft quantization, and the importance network, the one that they call it there, the important maps. They also use the feature extraction in feature map coding. And then the best PSNR. PSNR is peak signal to noise ratio. It's like how much, it's also the same, the image quality, almost the same with SSIM. And then they use the HEVC coder as their base. They just do the CNN here in interrupt prediction part, and also before the entropy coding here, CNN in loop filter. Means like they find which residual is the best by using the CNN, by extract the features on that. And then the next one, this is the pioneer. It was developed by a Google researcher, the end-to-end optimized image compression scheme. They use the GDN network and the convolutional layer also. So they learn all this. So this is the pioneer of the deep learning in image compression. And then this is the result of the Bell's paper. We can see like what I'm researching is in JPEG 2000, and the Bell's already supersede it a little bit, and also already supersede the JPEG. But the little bit that he supersede also cannot beat the fastest JPEG 2000 or XVC, because we have that kind of drawback. And then the next one is they use the GAN, Generative Adversarial Networks of Extreme Lump Image Compression. Like the first one, they preserve the overall image quantity while generating structure of different scales. And then this one, they completely generating parts of the image from a semantic level. They use the semantic level map while preserving user-defined regions. And then let's see. And then the third one is the deep convolutional autoencoder based lossy image compression. Like this one is the normal one, and then they use the convolutional autoencoder. We have the upsampling, and also in convolutional layer, After that, the traditional one, the PCA rotation, the quantizer, entropy coder. So they combine the traditional and neural network because they want to save more time, right? So this is the result. The result that they got, the GAN, Generative Adversarial Network, is here. The GAN is here. And then the red one is the BPG. BPG is the better portable graphic, the one that used the intra-prediction HEVC. So it's the traditional one, no deep learning involved. And then what they do is the CAE here, the purple one, this one. So it doesn't supersede the BPG at all, the better portable graphic. So in the field of image compression, these ones still have long way to go, maybe 2-3 years later, when there's a lot of devices with GPU inside them, maybe people can use the image compression in deep learning. So the future of image compression, we need to have better result than BPG, the HEVC intra. This one is not done yet, and JPEG compression is done. And we need to have low computational complexity, which is yet to come. And there's a lot of ongoing research, like maybe we can try to use the RNN, the CNN, the GAN, autoencoder. Maybe we can combine the traditional one with the neural network. So what I'm thinking to do after this is I want to combine the traditional and the deep learning. Maybe we can utilize the GPU power that we have right now compared to previous years, because right now people are already evolving in the GPU. So that's all. I hope like this one give you a brief information on image compression. So before I end, this is just like, because all of you, most of you are women. I am the woman in AI ambassador in Japan. So I would like to have, if anyone in Malaysia to join this society, it was like developed by the one in Europe. So you can register there free of charge. You're welcome to do this. You can grow networking. Okay, that's all from me. Thank you very much.
Feel free to ask your questions anytime on Slido. I think the hashtag is AI-Maxis. So if that talk sparked any joy in you, maybe you can consider doing a fellowship under Ms. Rosen. Yes. Okay, next up we have two speakers from Maxis, Ms. Wu Tai-Hui and Mei Ching. And they're going to share about the failures, successes, and pitfalls of taking your first steps in deep learning, as well as AI on our deep minds. So can I invite the speaker?
Oh yeah, I'm a photo in. Okay. So hi all, I'm Kai Hui. I hope you're not too sleepy. I know it's a work day, but mine's more gonna like a story. It's less technical, so just sharing about, and it's more appropriate for those of you who want to get into AI, because it's my story about how I was a complete beginner and how I got into AI, why I got into AI, and how was it. So you know, you can learn a bit, and for those of you who are more experienced, maybe you relate to my story. So how did it happen? Oh, sorry, forgot. I thought it was like accessory or something. Okay, so my background is actually mechanical engineering. I have a classmate there from University of Southampton. So I'm a mechanical engineer, and when I joined Maxis as part of the scholarship program, serving my bond, and I was in more of a project managerial role. It was like in a software role, it was complete opposite of degree. By that point, there was an AI team, a small AI team, and I thought it was pretty interesting because I know about machine learning when I was doing robotics in uni, and I thought, you know, interesting, I'll try it. And I did a lot of deep learning courses on Coursera. That's about it. And one of the first projects that came to our hands was when the network team told us they have a problem. And the problem is that they currently, you know, Maxis has a lot of cell towers, so we have to do a lot of cell tower inspection. And what currently is being done is that the rigger will climb out the cell tower and then, you know, carry out manual inspection and list down some of the defects, like structural defects like corrosion, paint peel, cable dangle, and they also have to do inventory checking and check how many microwaves there are and how many antennas there are. So this is very time consuming. So what they want us to help it out is to automate this part. So to create an AI software that can automatically detect the defect. So sort of the plan is to have a drone that flies around the cell tower, it must circle it, and take a bunch of images. The images will then be fed into the AI software and automatically detect the defect to save time. So now we looked around and see what other people are doing in terms of these kind of use cases, and found Microsoft were doing something similar, but they have such like very close-up photos of the pipe, and the defects are rather obvious. But what we had instead was like this. So the cell tower is not even centered, and there's so much background noise, and depending on the lighting condition, you have different shadows on the tower, so this is very much less than ideal. So then we have to evaluate the project. Should we take up the project or not? And the problems that we had was that, firstly, we've never done object detection before. As I said, we're very new to this, so we have tried out like hobby projects. So we did image classification, we did some like normal densely connected neural network, but never object detection. We never used a cloud platform because so far it's hobby projects. We never needed like cloud computing, so it's all local computing. The third one is we don't know how to create the data because the hobbies would know that you get most of your data provided to you in tutorials, and in Kaggle competitions, you get your data given. But in this case, we have to create the data ourselves. The last one is, fourth one is the business basically told us that we only have about 4 months to deliver, and this is on top of the fact that we have our main role. So this is a side project. My main role is a project manager, so my team member wants an Android developer and wants an iOS developer over there. And so, it's a bit tight, it's a bit tight. And but when the business asked us if we could do it, we said, of course we can. But deep down, we're like this. Anyways, we took up the project and we call it Project Skylight because, the name is kind of appropriate. And the software that we were to develop is called Horus. So now what? We've taken up the project, now what? First thing first, we have to learn about object detection, right? So we went around, at that point, this was about same time last year, I think. So at that point, there wasn't a lot of object detection tutorial around. There was a lot of classification, because classification is almost like the first thing that you do, cat versus dog. That's the first thing that you do when you try to get into vision-related projects, but just not a lot of object detection. So we had to go around reading papers, go to GitHub, try almost every other code to see which one works. And I went to Coursera and Udacity to learn a bit about the theories that will help us understand and train the network a little bit better. Now the data, second part, data. And data, we use the software called LabelIMG. So LabelIMG is basically a software where you can draw the bounding boxes to label the defects one by one. So like in this case, corrosion here, paint peel there, so you draw them on one by one. Then we have first problem, how big should the label boxes be? The bounding boxes be? Because it's not like a ball, it's not like a cat, it has fixed sizes, right? In our case, the corrosion is all over the structure. So is it supposed to be this small, that it goes to every single one? Or if the half of the tower is covered in paint peel, do you just draw the entire thing? We don't know, we have to sort of learn along the way. So what we did eventually use is a convolutional neural network. So this is really good for vision. And what it does, the one that we use is YOLO. So what it does is essentially look around the image and try to find which part of the image is most likely to contain an object. And that's called localization, first part. The second part is a classification part where it tries to guess what type of object that is. In this case, a dog, a bicycle, or a car. We chose YOLO because the training time is supposed to be quick, and it can run on videos almost real time. And for beginners like us, it's very well documented, so that's very important. But when we did all of those, we put the image into the network, we got nothing. You can see, there's nothing. Surprised because, at the very least, you should get microwave. But when we look at the data, we went in and see what's the problem, we found out that Thanos snapped his finger. Because 50% of the data was essentially lost. Why? Because we went to look at the data and the labels has typos. So a bunch of like 5 to 6 labelers were doing the labeling job, and they had typos here and there. So corrosion becomes corrosion, paint peel becomes paint peel, and just capitalization would deem all these labels not usable because the network doesn't recognize the labels. Other than that, we have noisy labels, like the microwave was labeled as tower, and vice versa, tower was labeled as microwave. And some of the microwaves is not even labeled, so they're not labeled. In general, we have about 800 images, about 1.2K examples per defect, but 30% of it was lost because of typos, and a further 40% was lost because of mislabeling and unlabeling. So this is really bad. Yeah, this is how we felt. But eventually, we did some changes on our end as much as possible, and we finally got some results, like microwave and RF, the easy ones. So what now? We got some results. What should we do now? How do we improve this? So other than obviously sending the data back to the labelers and clean it up, relabel it, we also decided to try another network. So look at a graph like this, we found out that faster CNN, another type of CNN, is a pretty good candidate because it has better accuracy and it's especially good for detecting small objects. This is kind of what we need. Another thing is very flexible. You can change up the network backbones to optimize the performance. Back to data. So another thing is we realized that we don't have a lot of data. So data augmentation is a type of technique, a popular technique for you to expand your data set. What you can do is take dark images and make it lighter, light images and make it darker. So this also helps the network adapt better to different lighting conditions. Another thing is to do horizontal flipping, but bear in mind, you also have to flip the bounding boxes, all the coordinates. And at that point when we were doing it, we didn't have any libraries to help with that. So we had to write custom scripts for it. And we finally got some results. Like, yay! And let's take a closer look. You can see on the left is yellow, on the right is fast CRSN. It's interesting because both of the network got the exact same data, but so they sort of pick up on the defects slightly differently. And you can see, actually, we put up most of the defects, like paint peel corrosion, so it's pretty good. It's okay. This is interesting because the image is so dark, like a human eye probably will miss out that there actually is a cable dangle down here. So the YOLO managed to pick it up. So we also put a video through the network. You can see the mic waves are pretty stable, but the cable dangle a little bit finicky. So we still have to work on it. So what's the issues? The issues, one is called a false positive. So false positive is where the object is not there, but the network thinks it's there. So you see lightning around the back, it's wrong. And false negative is where the object is clearly there, like you see an antenna boom over there, but the network's not picking up, even though it picked up every other antenna booms. So when we look more closely at antenna booms, we found out that we have 157 false positives. So that's really bad because our test size was about 500. But when we printed out all of our false positives, we found out that, wait a sec, all of them are antenna booms. But 92% of them were not labeled. So when the labelers were doing it, they missed out on the labels. So immediately, if they were labeled, their precision would be 97%, and the recall would jump to 73%. Now I'm just trying to, this slide is just to let you know how important data is. I think Jan later will talk about how noisy label, maybe you give a solution to us. But yeah, so data is very important. Pay more attention to it. I'm gonna end abruptly here because of time, but just to reiterate a few takeaways is that in the beginning, it will take time. So for those of you who want to get to AI, don't get discouraged when the learning takes so long. And second thing is skills are transferable. We did the model is here to detect defects, right? But easily the solution, you can change it up to detect people, and you can put it in the retail center and do people counting. Mei Ching later will talk a bit more about how we expand our use cases. And lastly, just to have fun, it is quite fun. I'll hand it to Mei Ching. Yeah.
Hi, good evening, everyone. Isn't she great? That's my youngest engineer here, and she's the youngest engineer on my team, yeah? So, again, just a matter of introduction. My name is Mei Ching. I look after IT in Maxis, and I'm going to share a little bit about our journey in AI. So it's going to be a little bit more business mindset, and what we learn from it, as well as why it's important to us. So just a very quick one, how we ventured into the world of AI in Maxis, right? So in the beginning, it all started with actually the deepest part, which is the deep learning portion. We had a hackathon, and our team, we had a winning team, and the team was the winning, it was a big data hackathon, and the winning team actually came up with a deep learning model to look at a problem. The problem was about churn in Maxis. So the problem uses a Google deep learning model, and it was quite revolutionary, even though most of the management didn't understand including myself, right, didn't really understand some of what was going on, but it was very interesting and it challenged the way we looked at things. So the next thing, what did we do was that we then started to feel that this was a very important area. We went and did a lot of talking around it. We learned ourselves along the way. Our team actually did a lot of training. We went and talked about it in the managers meeting. I talked about cats in the managers meeting. Our team member Fahim talked in the Sunway event. And along the way, we found a pilot project. That was what Skylight, that was what Kai Hui presented just now. And then, that gave us an opportunity to experiment with new models. And then we continue to brief management of what are the opportunities that AI bring to us, right? So there was a lot of learning in that. The second half of that was really about then taking this and developing talents within the company itself, right? So we took it as part of our big data center of excellence in Maxis. And then we built the talents and capabilities. We understood that there was a lot to learn, both in terms of the data science and as well as the data processing and the algorithms around it. So we learned from partners, commercial partners available, cloud providers. And then we also started this idea of incorporating a new AI/ML Center of Excellence. That AI/ML Center of Excellence augments all the digital capability that we have. So the need to build this was very important for us. Where we are currently working now is that in addition to all these experiments, we are also scaling AI, and there are a lot of initiatives around this. So at a high level, the initiatives that we are working on is how to make it a product that we can bring to support our customers' insights as well as go-to-market opportunities. And those are what we call the highest level, which is to build a cognitive intelligence layer, which I will speak a little bit more about it because it's still work in progress right now for us. And also, how do we make it commercially viable? That means having pipelines in production, and how do we build AI on this from a commercial manner to support the business opportunities. So that is where we are now. So a little bit of the background. Okay, I think everyone has seen this before. Deep learning is part of AI. AI is actually a way of looking at business view of the whole entire issue and the application, how we utilize methods like machine learning and deep learning in the business area. So it gets more deeper into it. And of course, I find that it's quite interesting. The things that we are going to talk about in deep learning is, I will call it the forefront of technology from that angle. So just a few very high level, what's the business environment? So this was actually part of the materials that I briefed the management team of Maxis to actually say, what are the opportunities, what's going on in AI here? Every company in the world, in Malaysia, is all about AI. Every day we see a lot of this information in the news itself. So number one was that all the technology giants are actually building AI capability. If you look at all these things like models like AWS, Google Cloud, Azure, and then there is also things like areas of works like NLP, natural language processing, computer vision, which is what we talked about just now, as well as all these other machine learning APIs. The second one was that I think probably some of you are, or you know someone who's already working in startups related to AI products. And now these can be small products, can also be large products or other offerings. And most of the larger enterprise, like the Googles of the world, are actually having, and even some of the end companies, product companies, are actually having internal in-house capabilities, right? Things like people like this Grab and Uber and all have got in-house capability for machine learning. This was very interesting. And the third one was around there are a lot of use cases now, and most of the companies, the newer companies, the Chinese companies like Baidu, Alibaba, and Tencent, actually has got a lot based on everything in their company is based on AI technology. So it was very exciting. Not only that, there are a lot of things available. Most of what you hear today are actually open source, and that actually means that a lot of people can contribute to this area itself, from frameworks to contribution to a common learning format. So this has actually given a lot of opportunities for AI to proliferate on that area. On the last side was also very exciting, was that there was a lot of training now available. Most of the courses you can learn online, and as well as now cloud-based technology is available. We speak about how to do image compressing in a better manner. Those GPU and TPU is readily available in the cloud, although a mass amount of it is still expensive. So a lot of things around data and data availability was actually the current landscape environment. And this really opened our management's mindset about what are the opportunities. So I'll speak a little bit about these are the key areas that we are working on in emerging clusters of innovation in Maxis, and then I'll tell you what the examples where it started off. So one was use case driven. In order to get the whole entire wave going, I had to tell the management a story after our hackathon and says, what are the opportunities around this? And we had to tell it in a use case manner, because if we tell it in an algorithm manner, it was very hard for them to. So we had to tell the story, what are the use cases. So we did some teasers. I'll show you what are the teasers. And one of them was the opportunity on the drone one that came out as a suggestion from our network team. Second one was that we also have, as a corporate company in the environment, we have a lot of partners, we have a lot of software in our IT environment. When these vendors actually have got solutions and tool sets, as well as tools to help our data science and our AI engineers to actually look at data. So this is fortunate for us because we have the abundance of partners to be able to help us do that. And this actually gives us opportunity to maximize all the data that we have. I think as a write-up for my thing, imagine as a telecoms provider, one of the things that I wrote in my summary was that we have actually about 1.3 million apps that is actually served by our subscribers on a daily basis. That means that for our 13 million customers that we have in Maxis, we have you guys serve about 1.3 million different websites on your phones a day, and this creates a data record of about 5 gig per second. Right, so I've got a lot of data footprints of our customer, a lot, right? So, and that's interesting for us, right? Because if you can analyze that, you can give the customer a better experience and how we can optimize that experience. So this is where the part about pipelines are. Data is the fuel of all ML and AI models, and that was very important for us because from this data, then we could actually study the behavior of our customers to give them a better experience. Other things that we are, the right-hand side corner was actually things that we are currently working on. We are working on building a second brain. And my interest in the second brain is that I'm a very lazy person, so I want to be able to work something to be able to work 24/7, and so that I don't have to work so hard. So the intention of a second brain was that if we can make that intelligence available from a cognitive basis to be able to take all the data as well as all the learning and training, and to be able to teach things how and get data to be able to be useful. That will be the I call it the final frontier of data science itself. So we're trying to create that second brain. And as well as the last one was that people and partnerships. This was very important to us because when you are in a company and you have access to partners like AWS, Amazon and Google, it's quite valuable to use that opportunity because I still believe that no matter how hard we try, it's very hard to build everything from scratch. So this will help us scale some of the AI opportunities. So this was just a summary. So in the management meeting last year, I teased them with 4 use cases, right? And I thought maybe I'll just talk a little bit about each one of them. The first one was actually about how we can use these neural networks, or rather what I want to build the second brain. Well, look at retail experience, right? And Kai Hui mentioned that we're trying to take that to retail stores, look at people's face when they look at products, whether they're happy or not, the sentiment analysis portion, as well as also a bit of facial recognition. And this, I think you've seen in some of the applications starting to come up already. So this was quite interesting and was very relevant because we have a lot of retail stores and we could use it. The second one was that I did a bit of analysis and found that there are places or use cases in agriculture in Indonesia where they looked at images from drones around agricultural plantations, and they could identify where the crop needs work on because of the color of the forest and the density of that. So there was a bit of video processing, and I thought, let me share that with network. And true enough, network guys after the conference came up to me and says, wow, it's very interesting, we want to try and get this drone to analyze our towers, and we got that pilot project working with them, and that was very interesting as well. but it's true that she said that it's after hours, so okay, fine. The third one was actually about the churn analysis and recommendation engines. Again, this was a bit based on the churn idea of hackathons. And this was quite interesting because this is currently being used commercially by all Netflix, Amazon areas. And then the fourth one was that fraud and operations was that I teased the audience on a management team about actual about fraud and operations area, and that was more or less like for example, Google has a data center that optimizes power based on that. So there were a lot of things, and some of them bite and some of them don't bite. Okay, so again, we learn also from our partners like Amazon, who has got other things around fulfillment. And then we also learn from POCs and showcases. We tried commercial products, deep lens in people counting. We looked at our advanced analytics models. We looked at our clickstream data and tried to do a lot of analytics and as well as machine learning from them. And we also did a lot of collaboration with vendors. So we looked at our operational data, how we are doing, and we also did. We are also learning a little bit on machine learning and on our IoT, new IoT products and services. So there were quite a fair bit of things. And then we also wanted to focus on people. So I mentioned just now, these are the key areas where we focus on in terms of people, on what's next, what are the key areas they need to learn, both on terms of the technical area around data, but also around the machine learning and the deep learning technologies, as well as the new technologies around that. So this was our people plan for that. We also wanted the team to have a little bit of fun. So this was some of the ideas. I say how we're going to get trained people, and our team member went to AWS conference. They participated in the Deep Racer thing, which is something that AWS is trying to make commercial around deep learning, around some cool tools around that. And in the latest updates, where are we at now? We are still working on this. It's not fully mature. I wouldn't say that we are super mature yet at this point, but we wanted to ensure that we have products around AI that is based on data and deep learning, as well as machine learning algorithms, and that's around geospatial, that's around speech recognition, and we're still working on that now. As well as we wanted our people to also learn and have fun along the way, and we started to now harmonize some of the talents and skills around a big data center of excellence. So why it's important to us? Maxis business is around data and high-speed technology, around 5G. IoT has a lot of data for us, so it's very important for our customer. We are also working very closely with platforms and partnerships, as well as the cloud-based environments. A lot of this needs to be developed in a very agile manner, and that's why it was very exciting for us to put this closely with the business products that we have. And this is the last one. What we learned, what was our lessons learned? The journey is just the beginning for us. I still think that there's a lot of things that we need to learn. But three things that stands out. One was that it was very important for use case. I highlight a lot of things are very important for use case. Use case sell the business aspect of AI to the management, and this was very important. The second one is that coding, statistical skills, and data mindset is what I call what we need from a broad AI training. That was also very important, and all three are needed. Not any one of them is less. The last one was that leadership buy-in is very, very important on unlocking the AI strategy. I need to make my leaders be able to talk about data and as well as AI in conferences, and to be able to understand some of this is what is important for us. So that's a quick view of our journey on AI, and it was very exciting. Anything else that you want, you can ask me offline. Thank you.
Since we are having this AI talk this evening, I'm sure you are interested in AI somehow. So if you are interested in a career at Maxis, go to their website, Maxis. There's a career section. They have many verticals, and from what I've heard, it's quite fun working for Maxis. Next up, we have Dr. Jan Sauer, who's a data scientist currently working at the Center of Applied Data Science, CATS. He designs and delivers customized data science solutions to corporate clients throughout Southeast Asia. And he was previously a scientist at the German Cancer Research Center, where he developed data-driven approach to identify and personalize drug treatment plans for colorectal cancer patients. So Dr. Yan Sawa is going to talk to us about training deep neural networks on noisy.
Everyone hear me? Is this volume good? Because then I'm perfect. I'm just going to put this aside because I use my hands. All right, so thank you for the wonderful introduction. Thank you for having me here and for being here. I'll be talking to you about deep learning and noisy labels. But of course, there's always a context to this. It's not going to be a super dry talk about some random subject. The context to this is that this was a part of my PhD thesis. The broader spectrum of my PhD thesis, the goal was to analyze the drug effects on cancer patients. What we wanted to do was we wanted to develop personalized, patient-specific treatment regimens to be able to say this patient has this set of mutations, has this subcategory of cancer, is at this stage, so we need to give them this drug, then that drug, then that drug, and then ideally they're healed. Now, this involved several steps, obviously. The first is that you typically don't want to give patients experimental drugs because you might kill them. That's a bad thing. So, normally, the first step of any research like this involves cells. You take cells from a patient, you treat them, you see what happens. And the most intuitive way to analyze cells, and also the easiest actually, is with microscopes. You have your cells, you treat them, you look at the pictures. Here we see an example of what happens if we treat cells with different concentrations of a certain drug. We see at low concentrations, all the cells are still there. At high concentrations, they're dead. So the general pipeline, if you will, of something like this is you start by treating the cells with drugs. And I'm skipping all the biology here because I don't know it that well either. You stain the cells with certain colors because you want to be able to see something. And what that means is you want to see certain parts of the cell. You want to highlight whether a cell is alive or dead. You can do that with colors. Then you take microscope images. The next step, and this is the part that I'm going to focus on in this talk, is you want to segment these images. That means if we look at this picture of cells, this is great for the human eye. But a computer needs to know what it's looking at. It needs to learn that this little thing here is a cell, and that's a cell, but the rest of it's a background. So we need to basically paint the cells. We need to tell the computer where the cells are. Now this is a problem. Modern screens have a lot of images, upwards of 100,000 images. Our project had, if I recall correctly, about 50 terabytes worth of images, 3D volumetric images. I estimated if one person were to go through and annotate all of these images, it would take them full-time 1.5 years of only doing this, 40 hours a week. That's completely unfeasible. So we want some sort of computer that does it for us, a segmentation algorithm. And the key here is this algorithm should be unsupervised. Because if it's supervised, that means if we have training data, we're back at the original problem. Now, these algorithms exist for cells. They've been around for decades. They work wonderfully. There's no problem. But, we do have a problem. And that problem is biology. Now, I'm sure most of you are familiar with pharmaceutical companies, with how expensive drugs are, with how much money they put into drug research. The reason for that is only 10% of drugs that have any notable effect on cells end up having an effect on humans as well. Just by virtue of being more complicated than a cell makes it so much more difficult to figure out what drugs work on humans. Beyond that, you also have things like FDA approval or the equivalent in different countries, to the point where, and this is a number I'm quoting with a source because I thought it was phenomenal, a company spends on average $2.6 billion developing a single drug. That's 10 million ringgit, give or take. 10 billion, I'm sorry. So what's the solution to this? Well, the obvious solution is don't use cells. What else can we use? Recently, in recent years, what's become popular are organoids. And without going into too much biological detail here, organoids are basically mini organs. What you do is you take stem cells out of tumors and you grow them. And at some point someone discovered you can actually grow them into little organs. They don't look like organs, but all of the cells that you would find in a brain or in your intestine or in a liver or in a kidney will be there. But while drugs work well on these organoids, there's a 70% overlap between organoids and human patients, the pictures look like this. Effectively, every patient has different looking organoids because they're so complex. Every drug causes different appearances in organoids. So if we try to use the same unsupervised segmentation algorithms, we end up with complete nonsense. Sure, we see some organoids are well identified, but for most others we have outlines, partial outlines at best. That doesn't really help us. Now, if you've been following deep learning or machine learning news over the past 5-6 years, you'll know that neural networks have become very popular for image analysis. So what happens if we try to use these instead? Now hold up. I just told you that manually annotating images takes too much time. Now I'm telling you, let's use neural networks, notorious for needing lots of label training data. That sounds like a terrible idea. It's not, though. To understand why, let's take a step back from our context and let's talk about noisy labels. Now, we thankfully heard this wonderful talk about the project Sky, which highlighted that data is complicated. We're not talking about numbers or spreadsheets anymore. We're talking about pictures, videos, 3D things, 4D things. Humans can't annotate all of that accurately. They're going to get tired. They're going to get lazy. They're going to get fatigued. They might just write their digits differently. So I'm from Germany, and I'm going to show this. We write our 1 like this. Here in Malaysia, you write your 1 like this. So the first few weeks I was here, waiters at restaurants would get noticeably confused that I tried to order 7 portions of nasi lemak for myself. It took me a while to catch on that it was my 1. So we have the situation that humans might just label things differently because they don't know any better. So what happens if we look at a model of that? So some of you may know the MNIST data set. The MNIST data set is basically just a set of handwritten digits from 0 to 9. It's about 60,000 digits. They're a litmus test, if you will. It's a very simple task, a very simple data set. If your classification algorithm doesn't work on this, it's worthless. That's basically the purpose of this data set. So I asked myself, well, what happens if the labels are corrupted? What happens if they're noisy? So sometimes a 7 might be a 1, or a 1 might be a 7. A 0 might be mistaken for a 6. And like this, I defined a scrambling factor. And I said, what happens to a neural network trained on this data with scrambled labels? Now, what would you expect? What you'd expect is that as more and more noise is introduced to the training data, our performance would drop, not necessarily linearly, but kind of continuously. If 20% of my labels are nonsense, I'm not going to get that great of a performance anymore. The reality, as it turns out, is quite different. What happens is absolutely nothing. So I started perturbing these labels, 25%, and looked at what happened to a neural network. Same performance. When measured on the true labels, so the undisturbed labels, it turns out that the neural network still trains to near perfect accuracy. So I looked at 50%. What happens here? Again, near perfect accuracy. We're now at 50% labels being incorrect, known incorrect. It isn't until somewhere way over here at like 80% where we suddenly see a massive drop in quality. All of a sudden, the network goes from, yeah, I can classify this, to what is going on? And this is fantastic. This is very interesting. And I didn't get a chance to study it too much in detail because, as it turns out, one of the things you learn when doing a PhD is don't question the things you do too much. You'll go insane. If something works, accept it. The hypothesis that I have is that because neural networks are trained iteratively, meaning you have parameters, and then the neural network gets a picture, for example, and it changes those parameters just a little bit. Then it gets another picture, and it changes them again a little bit. What happens is it basically ignores the wrong labels. So my parameters get better and better and better and better. Then there's a bad label. Then they get better and better and better and better and better, and a bad label. And so on and so forth. It increases training time a little bit, but we still arrive at the same solution, the same trained neural network capable of correctly identifying digits. Or, as it turns out, pictures. So we're still at our old problem. How do we segment images if we can't use unsupervised algorithms and we don't have manually annotated training data? Well, let's use this phenomenon because we do have training data. Our unsupervised approach wasn't that bad. It wasn't perfect, but it was definitely better than 20%, right? So what I did was I used the simplest possible segmentation method possible. I looked at individual pixels and their surroundings. So I said, this is the pixel. Here's the 20 by 20 pixel box around it. What's it going to be? Foreground or background? And you can see some training labels are good, others aren't. This one is obviously a foreground, obviously an organoid, but the neural network is trained to believe it's not. What happens, not unsurprisingly at this point, is the network is capable of correctly segmenting images. So without any sort of manual annotation, it was able to take this as a training set to generate this. Based on visual inspection, a near-perfect segmentation of our organoid images, which is pretty fantastic. Because now we've got a system in place that lets us segment these images without actually having to manually annotate any of them. We've basically turned a supervised neural network into an unsupervised approach. But science is about honesty, so I want to talk a bit about the pitfalls here, because I don't want to sell this as like the perfect solution to every one of your problems. So the main takeaway is, and we can see this in many different data sets, is neural networks can autonomously identify faults. We saw it in the skylight project, we saw it in the MNIST data set, I saw it in other toy data sets, and in the images, ultimately. But the 80%, it's a really nice number. It makes you think, wow, that's incredible. But that's because MNIST is a really simple data set. Like, if you're, I'm not kidding, if your classification doesn't work on MNIST, throw it away. It's useless. If our data gets more complicated, if we look at more complicated images, that threshold takes a massive leap to the left, to 20, 30% scrambling before the neural network fails. So as your data gets more complicated, you're going to have to be more careful about what you annotate. Pictures of cell towers are very complicated things. I don't think that they're going to manage with a scrambling factor of 80%. It did work for microscope images, though, because microscope images, thankfully, are super easy tasks. You either have a black background or a colorful foreground. The difficulty lies in the texture, in the gradients, in how colorful that foreground is. So for our problem, and again, don't question your results too much, it works. It works for microscope images of organoids. However, it's important to keep in mind that this first step was fine-tuned to organoids. Meaning, again, I can't even throw it at other microscope images without changing it again. It's a minor tweak. It's not quite as time-consuming as actually annotating images, but nonetheless, it still does require expert knowledge to handle and maintain. A more general approach, and I never got a chance to try this, would be to maybe edit or fix labels iteratively, so that I only fix labels that I know for certain are wrong, but I leave a portion of them untouched. If they could be wrong, they could be right, and I sort of change them gradually rather than in like one step. The last point, and at this point some of you might be wondering, hang on, he just showed us a neato algorithm and now is the conclusion. What happened to performance metrics? We're in a bit of a weird catch-22 here, because in order to show you performance metrics, I need a ground truth. I need labeled data. But if I had a ground truth, I wouldn't need this. So this put me in a really awkward position, because now I had to present this incredible, like, functional thing without actually being able to show how functional it is. Now, thankfully, my supervisors were biologists. They couldn't care less about this part of my thesis, so I sort of slid under the radar with it. But of course, formally, if you want to put this into production, if money, if lives depend on this, because, you know, cancer research, you're going to want some clever way of validating these results. Now, what I used and what I got away with was a downstream validation. So I took my segmentation results, analyzed the data, and if those results made sense, I just kind of assumed the segmentation was also more or less correct. That, in combination with visual inspection of like a random sample of images, was good enough. Welcome to academia. All right, so that was the end of my talk. Thank you for your attention. I hope you learned a little bit. I will be around for the networking session later if you have questions. Thank you very much.
Now we will have our Q&A session. Please, the speakers, can you come to the front while Niti from Maxis will moderate the Q&A. Again, if you haven't got it in the beginning, we are gathering questions on Slido, S-L-I-D-O, and the tag is AI-Maxis.
Hold on, network problems.
While we are setting up, I would just like to briefly summarize. We just had Dr. Yang who talked about using deep neural networks to train noisy labels. And before that we had Kai Hui and Mei Ching, head of IT, who talk about their experiences doing AI and machine learning in Maxis. And before that we have Ms. Rosa, soon to be Dr. Rosa, who talked about image compression. So anybody has any questions for us to ask?
Good evening, everyone. Again, welcome to Maxis. So we're going to have the Q&A session now. My name is Viti. I'm part of the Young Talent team as well, together with Ming. So we do have a lot of questions actually. So we'll try to go through some of them so that you can get a better understanding from our esteemed speakers. So maybe let's go to the first question. Do we need to master machine learning before going for deep learning or AI? Or how are they related to each other? Who wants to take this question?
I can do a short answer. The answer is probably no. Machine learning and deep learning are different parts of it. As I mentioned just now, there are machine learning algorithms and there are deep learning algorithms, but they're all related to part of the bigger picture. AI is a business application of machine learning and deep learning. So the answer is no. You can master each one of them individually.
So in my experience, at very least, I did deep learning on convolutional neural network. It was completely different from machine learning. I just jumped straight into it to run a project. And in terms of deep learning, there's so many types of different neural networks, like CNNs, RNNs. It's all different. You can, if you're interested in vision, you just go straight to CNN. If you like NLP, just straight to go RNN. You can't do that.
There you go, you heard from the expert. So the answer is no. Alright? In short. Okay. So next, in deep learning, do you need to consider the pixel size?
Yeah, I think so. We need to consider the pixel size because it will, if you don't have, you have a very large pixel size, it will take a lot of time to train the data. So you need to make it smaller. So it's necessary.
Okay. The third question is, who owns your customer data if you're planning on monetizing the data you're capturing? Wow, this is a very political question. If Maxis is benefiting from customers' data, the customers should be... okay, the person decided not to complete the question, but... Okay.
I can answer that one
Yes.
pretty quickly. We are not allowed to commercially use the customer data. We can use the customer data to analyze it for our operational purposes. So there are data privacy rules in each and every industry for us.
Yeah. So would the person who wrote this question want to identify yourself? We're not going to do anything to you.
Just to help everybody understand, the business environment is that you can actually anonymize data and you can use it for, let's say, behavioral. Let's say 50% of the people do something XYZ, but you cannot say that you as a person is doing this at what location. So if you anonymize the data, it's okay to use it.
Okay, cool. So the next one is, okay, I guess it's a statement. Wow, I can totally relate with your journey on starting a project on neural networks. Okay, with 3 hands.
So say thank you.
The next one is, what has Maxis learned to date about the high customer churn? Again, very political, interesting audience questions.
I think if we are perfect and we are able to say that I can avoid to have 0 customer churn, that is impossible. So what have we learned about it? Our churn rate for prepaid is very high. And our churn rate for postpaid is a little bit less higher. A lot of the churn rate is also impacted by the outside world, and those data it's not so easy to have. Let's say, for example, our competitors come and have a new type of plan and all, or something happens, right? Regulatory introduces something or that in that manner. So it's still very hard to predict very accurately. Otherwise, everybody would be 100% loyal to Maxis and there's 0 churn. So it's not perfect yet. So we're still building the right models. We're still learning from the model how to improve the churn rate. How to improve the retention rate of the customer.
Thank you, Mei Ching. We'll move away from Maxis, and then we'll go to a question for Yan. Yan, what would it take to commercialize the kind of research that you do?
Oh gosh, more money and patience than most people have. So this question has 2 answers, I guess. If you're talking about commercializing medical research, you're talking about patient rights, you're talking about data access, you're talking about who can use this data and how. So commercializing it is always a bit of a tricky thing. I don't know if there's a real answer to that. It's all it's rooted very, very firmly in academia and in the medical sector. If you have a breakthrough idea, if you do happen to find a way that you can segment images, for example, in a completely unsupervised fashion, all it would take is a startup grant. That deep learning startups are really in right now. And if you have a thing that works well, that can be applied in multiple industries, go for it. A prototype will be more than enough if you can show off that it works.
I just wanted to add that and put a question also to Yan is that I think this area is very interesting because there's a lot of news about how Google uses their technology like DeepMind to actually help the medical sector in order to detect patients with cancer early detection for some of this. And so I was wondering how mature is this area to becoming very commercialized, because that's very interesting, because once we get to that area, we're really able to save lives, in my opinion. And so
So the technology itself is very mature. It's very capable. We consistently hear reports about computers outperforming doctors when it comes to identifying cancer, especially skin melanomas. In terms of commercialization, again, you have the issue, how do you get the patient data to train a thing into the industry? There's that bridge you can't really ever cross. So again, you would have to take the idea out of academia somehow as a separate thing without the data. So however you facilitate that, I don't know, that probably depends a great deal on where you live.
All right. We will give a chance to Kai Hui to comment on one question. So the question for Kai Hui is, did the drone project have problems with weather conditions changing image characteristics?
We have not yet tried it on like actual real-time detection. So, but the accuracy, because we've been training on both dark and bright images, I don't see a preference for like bright images and dark images, or the accuracy drop with dark images. I think the key idea is to have consistency, like, you know, if the distribution in the training set has to replicate the testing set. If you only have bright images in the training set, if you have dark images in the testing set, it's not going to work. So just make it consistent.
Okay. The next one is for Rosa. Does deep learning compression performance depend on the content of the image? Example, could pictures of cats be easier to compress than pictures of dogs? Wow, okay, interesting.
Wow, it's very interesting actually. But I think it will not depend on the content of the image, because usually it's the image size and then like the pixel number, something like that. So it will not depend. It's usually independent.
Engineers like to ask funny questions. No, I'm an engineer myself, okay, so I understand. Okay, next one. This is an interesting question. How do you choose who you want to do the Sky Eye project? Isn't there other employees who want to do it as well, but do not get chosen to do it? Sorry? It's a Maxis employee.
Please come and talk to me after this. You got an all-night job after that.
Why didn't you tell us earlier?
Yeah. But maybe I can also answer this. I think this one, it really depends on you as well. If you really want to do it, you should go and do it. You know, there's so many tools, so many free tools out there that you can go and try. And if it works, great. It's even better for the company and good for you. So really, if you want to do it, here in Maxis, if you really want to do it, you can go and do it. You know, there's like Kai Hui, you went and tried it, right?
And you try it, you don't just try it like, you know, don't show them about cats and dogs. That's be relevant to the use cases, right? I mean, you don't go to your boss and show them, oh, I can classify cats. No one's going to care.
Yeah.
So you have to do a relevant use case.
Yes. Cool. Next. Okay, this is for Jan. What segmentation architecture did you use?
A very, very simple one. So the problem again was time. We had hundreds of thousands of images, and if you use a large architecture, every second counts. Meaning that my goal, like the first half year of this project, was to really figure out the absolute minimal architecture I could find to make this happen. And what it landed on was a custom architecture that basically split the image. So the image consisted of 3 channels, red, green, and blue, split each of the channels, ran independent convolutions on them, and then a final fully connected layer at the end on all of them at the same time. I think it was 4, 5 layers deep, so nothing worth calling home about.
Okay. There's an interesting question here about Mr. Yan. Did you pass your PhD though? But I will not ask this question. Yeah. For your information, for the person who asked, he did pass his PhD.
If you're concerned, you can get away with quite a bit, don't worry.
Okay, this is an interesting one. Are you going to get any of the new Google Coral offerings? If so, any tips for how to get it to Malaysia? I'm not sure who can answer this.
I cannot answer it.
It's so difficult that none of the speakers can actually answer.
I need to Google what's Google Coral.
Anybody the person who asked this question, do you want to clarify? Yes.
It's the new TPU offerings from Google. So there's a Raspberry Pi thing, and also a USB Edge CPU thing to run your models on.
Okay, so the little bit of advertising for working in a company is that when you're in a company and Google wants to partner with you, they will give you a lot of these free services. So we're actually doing a planning session with them next week, and we actually have a thought about using some of these new capabilities that they have. Right? So we've got a couple of guys who are very good at Raspberry Pi as well. So if you're interested, come and talk to me.
Okay, this is a general question. How can someone enter AI without prior postgrad education?
I'm the only one without PhD here. How do you enter? I mean, it depends on the level, right? I think the one that we're doing wasn't like a full-fledged production project, right? It was a POC or proof of concept. So stuff like that, a lot of hobbyists is doing it. I mean, I'm an engineer, a mechanical engineer, but I've never actually built a car. I mean, I study about it, but never built it. So this case is a building thing. It wasn't study about they're going to details, the math, and then Jan is doing a lot of breakthrough research. Instead of starting a project, you don't need a PhD, unless your boss wants it. That's a different story altogether.
Yeah. So I can add a bit here. If I look at the distribution of educational background in the CADS, where I work, the Center of Applied Data Science, we have 2 PhDs, myself and someone else. We have everything across the board, from electrical engineers, chemical engineers. We have a few business people in there who somehow found their way into AI. So the getting into AI is a very broad thing, because you could talk about machine learning, you could talk about data engineering, you could talk about even DevOps, turning machine learning code into production. There's so many different things you can do that a formal background isn't, unless you're aiming at a research position. Postgrad background is not important.
Yeah, and to add on, I think we are very fortunate that we live in the era of internet, and there's so many free courses on Coursera, on Udacity. There's so many, I've seen so many. You can just go and do, and I think in 1 or 2 months you'll know this, So it's just go and do free courses.
I think also to add on to that is that there are, like what BT is saying, there are a lot of courses in Coursera, but the most relevant experience is actually hands-on. You have to try, right? And you have to try and be frustrated, in my opinion. Right? So I actually quite appreciate the stories that we have of people who learn PhD and people who don't learn PhD, because you have to try and you experiment and you understand how it works then.
Yep.
The thing they keep telling us about the PhD is that the most valuable skill you learn is running a project. It doesn't even have to do with what your field is. So again, you have the hands-on experience. If you run a project, if you've made something, that's just as good, if not better.
Okay. We'll take 2 more questions. I believe this is for Rosa. Why is decibel used to describe an image quality, and how does lower frequency block signify more useful information?
Okay, the decibel is actually a measurement for the PSNR. It's like how many hertz, how many decibel it is it's usually used in image quality. And then after that, what is it? The next question.
Oh, sorry.
How does lower frequency? Okay, lower frequency usually is a detailed information. It's a well-known one. So it's the high frequency, you can see if it is in the wave side, the low frequency is like this, right? And the high frequency is like this. So if it is like this, then it will be a lot of noise. I think does this answer the question? I think answer right.
Okay. And the last question, the most interesting question of the night. How can I be part of those Maxis AI related projects?
Come and talk to me.
Ladies and gentlemen, that concludes our Q&A session for the night. Thank you so much for participating in this.
Thank you, and thank you all amazing speakers. Just a few notes before we end. Yeah, so I just want to shout out to all the sorry, suddenly lost of words. All the volunteering people around here. We have Chilia from DevOps in Golang doing live streaming and recording for us. And we also have women tech makers, Kamra, who is also holding an International Women's Day event. And actually, she has brought with her a demo.
Oh, yeah.
A very interesting demo, AI related. And she's going to show you.
Okay.
So you can come to our International Women's Day party and also attend the Women Tech Magazine. I think you will come to get back to your seat so you can watch the video.
Okay. 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 So tonight, everyone's been talking about, CNNs, but for International Women's Day, Women Tech Makers, we're hosting something called artificial intelligence. So using neural networks in a more creative way. And what we've done is we've partnered with 5 very good Malaysian female artists to share their work in a new visual way using artificial intelligence. And here's a sneak peek. Okay. So it algorithmically repaints the image in the style of the original artist. And we're doing that with 5 Malaysian artists for International Women's Day. And if you want to know how to do it, you can come to our event at Google on the 30th of March. The link is in the Facebook on how to apply. And we're doing a code lab on how to, implement this, so you can do it too. Thank you.
Thank you.
Okay, that's it for our event tonight. Thank you very much for staying with us. And one last request, can we have a nice, beautiful photo of everybody right up in the front?
Yeah, so normally what we'll do is we'll get everybody to come to the front and we'll take the picture from the top.
Okay, so everybody to the front,
SOP.
please.